Imagine glancing at your watch. With normal vision, reading the time is simple. With refractive errors, such as presbyopia, the watch appears blurred without eyewear. As one ages, eventually bifocals will be needed for such simple tasks. In this work, we propose correcting optical aberrations of the eye without the need for eyewear by modifying the composition of the displayed imagery as well as the underlying display hardware. Using this approach for the watch allows a sharp image to be formed. However, prior methods produce low contrast images. In this paper, we enhance the contrast by introducing additional display layers, together with a new image pre-filtering algorithm. Here we illustrate a viewer with presbyopia viewing a conventional display, for example an LCD panel. As the degree of presbyopia increases, measured in diopters, the perceived image becomes increasingly blurred. Optically, this is represented by a point spread function that increases in diameter. We model the blurring process as a convolution of the displayed image with the point spread function. In prior work, a pre-filtered image is displayed to correct for defocus. This image is produced by deconvolving the original image by the point spread function. While restoring sharp vision, contrast is significantly reduced. We address this limitation by introducing a multi-layer pre-filtering framework. With the addition of a second layer, we show that multi-layer deconvolution can similarly restore sharp vision, but with significantly improved contrast. In practice, only a small gap is required between the layers. Here we compare the performance of prior single-layer methods versus our multi-layer method. Single-layer methods not only reduce contrast, but also produce ringing artifacts. In practice, these artifacts are masked by the low contrast. A second benefit of our method is to eliminate ringing. We show 3 simulated results with natural images. Here is the original image, the blurred image seen by the viewer, the pre-filtered image displayed on the screen, and the perceived image. Here are the pre-filtered images for a 2-layer display and the corresponding perceived image. As for the eye chart shown before, contrast is enhanced and ringing artifacts are eliminated. Here we consider a second example. Notice that pre-filtering allows the face of the coin to be read. Also notice strong ringing on the face is eliminated using 2 layers. Here we show a final example. We assess the real-world performance using a 2-layer LCD prototype. Images predicted by simulation and captured with the prototype are compared. Here we compare the blurred images, the single-layer results, and the 2-layer results. In the paper, we describe deviations due to the physical hardware. As with simulations, contrast is enhanced, and ringing is eliminated with 2-layer processing. We again compare experiments to simulations, showing close agreement. Our method can also be applied to correct videos. Here are the original and blurred videos. Single-layer pre-filtering restores sharp vision, but with strong flickering artifacts. This is due to the rapid variation in the dynamic range required to display the pre-filtered image. As described in the paper, we introduce a simple temporal normalization procedure to eliminate flickering. This method also applies to 2-layer displays. As plotted in blue, the required dynamic range varies significantly less with our 2-layer method. This allows contrast to be further enhanced beyond that achievable with single-layer methods.